Hello everyone. In this video, we'll be looking at mathematics for gaming. Let's first look at 2D and 3D coordinate systems. So in a 2D coordinate system, we can determine an actor's position based on the X and Y axis, left or right, and up or down. In a 3D coordinate system, along with X and Y dimensions, we can determine an actor's position based on the Z-axis. This Z-axis gives us a conclusion on the depth. So 2D coordinate systems are formed by two mutually perpendicular axes. These axes intersect at a point which we call the origin. The coordinates of any point in the xy plane are determined by two real numbers, x and y, which are orthogonal projections of the points on the respective axis. The 3D coordinate system is formed by a point called the origin and a basis consisting of three mutual perpendicular vectors. The coordinates of any point in the space are determined by three real numbers, namely x, y, and z. When we look at rotations in the 3D space, in the real world, there are three types of rotations in an object which we can name yaw, pitch, and roll. So these rotations are defined as the pitch is defined as the rotation on an object about the y-axis. Yaw is defined as the rotation of the object about the z-axis, and roll, rotation about the x-axis. So if we represent this graphically in a real world scenario, we can see how these rotations of an object work by looking at how a plane can rotate. So we can see here we have the pitch, roll, and yaw. So these are rotations in the 3D space. Let's talk about scalar quantities and vector quantities. When we talk about scalar quantities, these have a magnitude only. For example, speed or distance or age. These we know that they have only a magnitude. There is no direction as such which we can accumulate to this amount. However, in contrast, vector quantities have both a magnitude and a direction. So when we take velocity as an example, we can say that the velocity is 35 meters per second and the direction is north. So you have two things, two factors which we need to consider when it comes to vector quantities. So we know that a vector quantity is represented using an arrow above the symbol that we use to represent this vector quantity. So we can say velocity is a vector quantity, hence the arrow, and we can give the magnitude and the direction. So when we have the magnitude of a vector quantity, basically how we compute the magnitude of a vector is, how we denote it is this. So let's say we have a right angle triangle. So this is A, this is B, and this is C. So we know by the Pythagoras rule, Pythagoras theorem, that A squared plus B squared is C squared. So with this formula, we can compute the magnitude of a vector Say, for example, we have a vector v you have a vector v, and you have two other vectors towards the x direction vx, y direction vy. So when you are given these two vectors, when you compute the magnitude of the vector v in terms of a right angle triangle using the hypotenuse, we know that the magnitude of this vector is equal to vx squared plus vy squared, square root of that entire thing, because over here c is equal to a squared plus b squared, square root of that entire thing. So this is how we calculate the magnitude of a given vector. And then when we talk about vector normalization, normalizing refers to the process of making something standard or normal. In the case of vectors, let's assume for the moment that a standard vector has a length of 1. A normal vector has a length 1. To normalize a vector, therefore, is to take a vector of any length and keeping it pointing in the same direction and change its length to 1, which is to say we are turning it into what's called a unit vector. So let's say that you have a vector of length 10. So this is a vector of length 10. In the process of normalizing, in this process, we take the same vector pointing towards the same direction of length 1. In other words, the unit vector. Since it describes a vector's direction without regard to its length, it's useful to have the unit vector readily accessible. So for any given vector v, its unit vector is usually written as this. The unit vector is calculated in this way. So given a vector v, the unit vector of v is equal to the vector divided by the magnitude of that vector. This is how we calculate the unit vector. In other words, to normalize a vector, what we simply do is divide each component by its magnitude. You divide the vector by its magnitude in order to calculate the unit vector, or in other words, to normalize. So let's say for example, that we have a vector of length 5. Then what do we do to normalize it? We divide 5 by 5, which gives us 1. So if we look at our right angled triangle, we then need to scale the hypotenuse down by dividing 5. In that process, the sides shrink and divided by 5 as well, which is to say, this is my right angle triangle. These are the vectors. So when I want to normalize this, this side is 5 over 5, this side is 3 over 5, and then we have 4 over 5. This one becomes the unit vector. Now let's look at the operations that we perform on vectors. So we have vector addition and subtraction. So addition complies the commutative law and subtraction is not. And then we have the negation of a vector, which is basically we take the opposite. It's the same magnitude but in the opposite direction. So the change in the symbol, positive or negative, tells us that there's a change in the direction. And then when it comes to the zero vector, there's a zero magnitude and it has no direction. Now let's come to dot product and the cross product. So let's first talk about the dot product. So we know now that a vector has a magnitude and also a direction. And say we have two vectors as such, two vectors like this. Now they can be multiplied using a dot product, or we can multiply them using a cross product as well. We will discuss cross product next. So dot product is written using a central dot, which is to say, if this is vector A and if this is vector B, the multiplication between these two becomes A dot B, which basically means A and B. So how can we calculate the dot product of these two vectors? This is vector A, this is vector B. The angle between them, let's say, is theta. What is meant by this is vector A is that the magnitude of this vector is A, which is the length, and the length of this is B. Okay, so A dot B will be equal to magnitude of A, magnitude of B into cos theta, the cos of the angle between A and B. So we multiply the length of A times the length of B times the cosine of the angle between A and B. This is how we calculate the dot product of given vectors. Then let's look at the cross product. So here, when we have two vectors, the cross product of these two vectors is another vector that creates right angles to both these vectors. So A cross B creates a right angle with this and also with this. And it happens in 3 dimensions. So how can we calculate this? Here A cross B is equal to magnitude of A times magnitude of B times the sine of the angles between A and B. Now let's look at scalar multiplication. To multiply a vector by a scalar, we need to multiply each component of the vector by a scalar. So if the vector u equals u1, u2 has a magnitude of this and a direction d, then nu, if n is the scalar, nu is equal to n u1, u2, which is to say nu1, nu2, where n is a positive real number. The magnitude of nu will be calculated in the same way, and the direction does not change. So the direction will be the same as before d. But if in case n was a negative number, then direction will be opposite of d. So if we look at an example, say if u is -1, 3, and if we want to scale this by 7, 7u is equal to 7, which means -7, 21. Okay, so there are several properties when it comes to scalar multiplication. So the properties of scalar multiplication are the magnitude of the scaled vector is equal to the absolute value of the scalar times the magnitude of the vector. Magnitude of the scaled vector is c. Say for example, if v is the vector and c was the scalar, magnitude of the scaled vector is this. This is equal to the absolute value of the scalar times the magnitude of the vector. And then this complies the associate property. If u is the vector, du is equal to cdu, and the commutative property holds, and then the distributive property holds, the identity property. Now let's come to usages of vectors. So we can represent a sequence of displacements using vectors. Say you started from here, you came all the way up until here. So that's the distance you traveled. Your displacement is the distance between this point and this point, the direct distance. So this displacement can be denoted using vectors. Moreover, you can have multiple coordinate spaces, which we'll be descriptively talking in the next couple of lectures. In multiple coordinate spaces, the coordinate space maps different coordinate systems, and just by multiplying a vertex by a particular matrix, you can convert the vertex into a different space.